time to get started. We'll have a quiz on Monday. Also, lab reports, the Shaken Not Stirred due here in class on Monday. Quiz will cover everything up to what we get through today. Since test 2. So that includes resonance, Diene reactions, substitution, mass effect. Okay. All right. Beta elimination. We're looking at an example reaction. We did a mechanism. We did an E1. We showed a primary carbocation that looked pretty bad. Let's do a mechanism E2. So what's another mechanism we can show to get to these products? Different mechanism. So instead of this ionizing off, if this ionizes off, and cation, we're essentially doing that mechanism up there. So what's another way we can get these products? Well, I'll just go ahead and show you. Another way we can do this is, instead of this ionizing off, what if these electrons come in here? What are we trying to do? Well, this is going to take an H, right? Leaving group's going to leave. We're trying to put a double bond in, not substitution. We're not going to come in here and do a SN2 and kick, and this is not going to bond here, but it says I'm taking H. Well, we could do it like this. What if this takes the H? These electrons move in to make pi bond, and that gets kicked off. 3 arrows, all in the same, just one step with three mechanism arrows. All these 3 steps being concerted. What would that give? Give all that over there. That's it. Base takes the H. On the end, base has the H. These electrons fall in to make pi bond. And that carbon can't just make another bond. Something has to leave. Well, the leaving group leaves. And the electrons move on to the bromine. And we produce this. So, is this the same mechanism as we showed above? No. Above, we first showed ionization. This is a different mechanism. This is an E2. It's concerted. There's no carbocation here. It's similar to when we do backside attack. The nucleophile comes in and bonds and kicks off the leaving group at the same time. Well, this is sort of like that, except it's not coming in here and kicking off the leaving group. It's taking an H, and these electrons move in and kind of kick off the leaving group. So no intermediate. There we go. No intermediate. There's only a transition state. If we did a reaction coordinate diagram, I'll be brief and won't label these appropriately. We have some type of starting material. This is our alkyl bromide. We go to product. Would you put this higher or lower compared to this? Huh. Is this reaction thermodynamically favored or not? Going from here, 2 sigma bonds, now we have 1 pi bond. Is it thermodynamically favored? It's actually not. The product is actually a little higher in energy. You can pull out your calculator and do this. This reaction is actually most likely endothermic. Doesn't mean we can't do it. Maybe we have to heat it some. Do we have any intermediate? No, there's no energy well here. It's just a transition state. So it's boom. And this is your activation energy, right? And this is your transition state. What does the transition state look like? I'm not going to draw it, but it's where this bond is forming. This bond is breaking and forming, and this bond is breaking. So it's lots of sort of partial bonds, all happening at the same time. That's why we All this is concerted. This bond is forming in the transition state. This bond is partially forming. This bond is partially breaking. This pi bond is partially forming. This carbon-bromine bond is partially breaking. All that's going on in the transition state. It's kind of a high energy. It's not a discrete intermediate. So we don't have an energy well. It's only one transition state. This is your classical E2. Okay, concerted beta elimination. All right, of your two main reactants, your substrate relieving group and your base. So here we call it a base because it's taking an H. If that had attacked here and kicked off the bromine, we would have called it a nucleophile. Okay, of your two main, which ones are involved in the rate determining step? Well, which is the rate determining step? That one. There's only one I showed. There's one step. Okay, are they both involved in the rate determining step? Yes, they better be, because that's the only step. That's why I call it E2. It's called bimolecular. Where in our previous example mechanism, the rate determining step only involved ionization of this. That had nothing to do with it in the mechanism we showed up there. That up there was an E1. First step of E1 is the same exact as the first step of SN. So, this is concerted beta elimination. It's analogous to concerted backside attack with your SN2 substitution. The base abstracts the beta hydrogen, though. Okay? Now, since this is involved in the rate determining step, the base needs to be strong. Just like with an SN2, the nucleophile needs to be strong. Okay? So this E2 does require a strong base, and we'll state that below. So of the two mechanisms, which one is appropriate for the model reaction? We've already really answered that. Okay? E2. Because up there, you don't want to make a primary carbocation. This model reaction is classical. You should look to be able to see this and say, hey, this has got to be an E2. To eliminate, what are we essentially removing from this molecule to make that? Minus HBr. But we put that into the parentheses. Because it doesn't form HBr. But that's what's removed from here, essentially. We eliminate HBr to make the alkene. It's an elimination reaction. Okay. There's actually a third possible mechanism we could show. And I'm going to show it. And it's not going to be E1 or E2. But it is a third possible way, and I want to show it because I want to make sure you don't try to show this yourself later on. Does anybody have another mechanism we could show? Other than the first E1 or E2, those two. What's another way we could get to these products? Well, let me go ahead and show you. I'm going to show you a third way, and let's make sure you realize it's different from the two ways I've shown above. What if the base takes the H and just leaves the electrons here? That would give bromine. What's now here on this carbon? What does this arrow mean to you? These electrons moving onto the carbon as a
Negative charge.
negative charge, but what else?
A long pair.
Long pair. That's what this arrow means. These electrons just move, they're not falling in to make pi bond, they're just sitting here. And that's a negative charge. Plus what? Plus our alcohol, which, okay, there we go. We just formed our alcohol. So check. We're trying to form all those things over there. Here I'm showing a carbanion as a discrete intermediate. Did I show that in mechanisms 1 or 2 above? No. So this is a different mechanism, okay? So this is an intermediate. Now, what if we did take these and move them in and kick off the bromine? What would that give? Well, we move these in, make pi bond, and then we kick off the bromine. So this would also give these products. Here I'm showing a carbanion intermediate. First one showed a carbocation intermediate. That one showed no intermediate, everything happening concertedly. This showing an intermediate but carbanion because we showed the base, the acid base taking place first. Well, this is actually a known mechanism, but it doesn't occur with anything we're going to see here in organic 1. Okay? This doesn't occur because this is not good. It's too high of energy. Typically, carbocations are relatively easy to make. Positive carbons are easy to make. Carbanions are much more difficult. You're only going to make this carbanion if this is very acidic for some reason. And there'll be special cases where this may occur. But here's the important thing. First off, if you did this, this would be the rate determining step. Then, this moving in and going back to a neutral product would be fast. Here's a big difference between the two and then this one. E1, look at your mechanism. Does the leaving group leave in the rate determining step of E1? It does, yes. What's the rate determining step of E1?
Ionization.
Ionization of the leaving group. Leaving group leaving. Yes. Does leaving group leave in the rate determining step of E2? Yes. Yes. But look at this. In this mechanism, does the leaving group leave in the rate determining step? No, it does not. And that's important to when you assess and understand mechanisms. Okay? Now, this may be revisited in organic too, because there's a time when this is more appropriate. This is actually called an E1CB, with CB I think stands for carbanion. But I'm never going to say anything about that mechanism again. We're going to look at either E1 or E2. Okay? All right. Keep in mind though, this is going to take an H in the E2, but it's never going to form a carbanion. It's never going to do just a simple acid-base reaction. It'll take it and the electrons immediately move in and they consert it. Okay? Consert it. Not stepwise to form a carbanion. Not here in this class with these E1 or E2. Okay, let's look at an alternative example. We can take this alkyl halide and just take neutral butanol and just heat it. Or you can actually do this with no solvent at all. Just heat this guy with no solvent. We can get this alkene plus HBr. Okay. Now this is clearly an elimination reaction because we eliminate HBr. Is it E1 or E2? Again, forget about the third mechanism. Does that look like E1 or E2? E2 requires a strong base. E1 or E2? E1, what? Because that ain't a strong base. What's a strong base? We said this back in August. Anions or sp3 nitrogen. No strong base. E2 requires a strong base. Just like SN2 requires a strong nucleophile. Okay? This is a classical E1. Weak base. What happens here? This guy's lazy. It's not going to come in here and take the H and boom. It's too lazy. But if you heat this, what can happen? What can happen?
Ionization.
This can just ionize off. Boom, boom, boom. Make cation. Okay? Plus Br minus. Under the right conditions, good leaving groups can just leave on their own. That's just called ionization. Again, you put HCl in water, what happens? The Cl leaves the H, it ionizes. This is facilitated by polar solvents. Just like the ionization of HCl is facilitated by putting it in water. You put HCl and hexane, it won't ionize. It stays covalent. Okay? Now we'll talk about how you maybe help promote this other than heating. You get this. That's your rate determining step. Now how do you get home from here? Well, you got to remove an H because there's two here. What can take the H? This could take it because that could act as a weak base, but you can also just have the leaving group take it, take the H and these fall in. And if the leaving group takes it, what do you have? This and this, and you see the solvent really doesn't do anything at all. And indeed, you really don't even need solvent. If you just take this compound and heat it, like maybe up to 200, 300 degrees, it'll start giving off HBr gas. Because it's doing this reaction. And you can test for the HBr gas, just hold some litmus paper over it, it'll turn red. So this is your rate determining step, and then this beta elimination from the carbocation would be fast. Okay? Forming the cation rate determining step. So this is a classical E1. Okay? Now this is the case where E1 would take place. Ah, can you do E1 on this? Can you make carbocation here? What type of cation did we make? Secondary, is that okay? Yes. Secondary is okay. You just don't ever want to make primary. Primary is pretty bad unless it's resin stabilized. Then it's really not primary. We'll talk more about that. Okay. Look at this. Look at this. We got something to think about as we go forward. Why did we take that H and maybe not one of these H's? Because couldn't we have taken this H and put the double bond in down here? So that's A. What if this had taken this H and put the double bond in there? That would have given this alkene. That's actually possible. Because you have beta hydrogens, that's the alpha carbon, that's the carbon with the leaving group originally. Alpha beta or alpha beta. This is going to be on the next page. But before we get to that, let's rationalize why. Why do you think that alkene was formed and not this one?
More stable. It's trans,
Lauren? Why this one? I'm sorry, why that one? What's an argument for that one? More substituted, more stable. More stable product, usually lower transition state leading to it. This is a monosubstituted alkene. That's a disubstituted alkene. Okay. Why trans? Why not cis? Same reason. Trans is more stable. Now you gotta be careful. We're doing E1 here. E1. And I'm going to give you just a preview of the next page. When we turn the page, we're going to cover this. Okay? Because look, it actually looks like it should be cis. Because right here, these two groups are cis. If that becomes alkene and these two groups are here, they would be cis. But guess what? You have free rotation. This thing's going to free rotate. Just back to free rotation here. If it has free rotation, are these groups going to prefer here or here? Yeah. That's going to rotate to trans and then eliminate. Okay. There's things in here. Thermodynamics. I basically covered that. This is actually an endothermic reaction because when you put in a pi bond, Making the alkene, you're actually going uphill because you're removing two single bonds and making a weaker pi bond. If you do calculations, you'll see this reaction is actually endothermic. Often eliminations require heat. You can do endothermic reactions. What about entropy? Is it favored? Is an elimination reaction favored by entropy?
Yes.
Let's just look at this one. Forget solvent. If this eliminates to form this and that, is it favored by entropy?
Yes.
Sure. One molecule breaking into two. So it is favored by entropy. But it's not favored thermodynamically because you're making a weaker pi bond. Make sense? The standard assessment of reactions. Okay. Here we go. Elimination has a bit more intricacies than substitution. And I alluded to it here. This alkene versus the other, that was regiochemistry. And also had stereochemistry, cis versus trans. So here's our systematic look at it. What about when regioisomers are possible? First off, if you take this guy and do a beta elimination, there's only one alkene possible. Because there is only one type of beta hydrogen. I'll just draw one in because the other one's identical. There's only one type of beta hydrogen. And so you just remove ACl, put the double bond in here. It's the only place. So it's the only regioisomer. And not only is it the only regioisomer, the only region you can put the pi bond, there's actually also no stereoisomer here because that alkene's not stereogenic. So that's the only possible beta elimination product you can show. But look down here. If this undergoes beta elimination in general, you have HA, but you also have HB. Now, of course, there's two of them here and there's three of them there. That's two different types of beta hydrogens. And if you remove this beta hydrogen in the chlorine, the double bond ends up on the end there. But if you remove this beta hydrogen in the chlorine, the double bond's going to be here. Right? So these would be two different regioisomers. Regioisomers have different names. But this regioisomer has a stereoisomer. Because the alkene's in the same position, it's just this alkene is Z where that one was E. So you actually have three possible products theoretically. Which one are we going to get?
One in the middle.
One in the middle. Here's the answer. It's only the one in the middle. Why? That is the most stable of the three. It's the most substituted and it's trans, so the bigger groups are further apart. That is the most stable of the three. But here's the kicker. You only get that product when you're doing E1. You only always get that product when you're doing E1. E2, there's much more to it. In E2, you may not get that product. Okay, I'll tell you again. Which alkene will be formed? It depends on a variety of factors, including mechanism. And the mechanism is going to include on which base you use. And the orientation of groups in your starting materials. Because we may have stereochemistry here. It's going to depend. The easiest is E1. But first, let's make some statements here, some terminology to describe these products. The most substituted alkene is the thermodynamic product. Compare these two, as a stereoisomer. These two. Which alkene's most substituted? That one, disubstituted. It's the thermodynamic product. That means it's the most stable product. Okay? The most substituted alkene is the most stable product. That has a name. In the context of this reaction, the most stable product, the most substituted, is called the Zaitsev product. Okay? So that's a Zaitsev product. Again, it does have a stereoisomer. Now, Zaitsev, nobody knows how to spell that. You'll see spellings, variety of spellings. Some books or people even spell this with a Z at the beginning. Zaitsev. I think it's Russian. I think it may be originally even a Z. I spelled it with an S, but you'll see different spellings. Okay? The Zaitsev product, that one in this case, it's always the major product in an E1 elimination. E1 is easy. E1 always gives the most stable alkene. All right, that's a take-home message. If we want to get into why, it's because there's really no restrictions on how the mechanism takes place. And since there's no restrictions, thermodynamics just rules. And since thermodynamics rules, you get the product with the lowest transition state, and that's typically the most stable one. The transition state leading to this one is going to be the lowest. Okay. But this is not the case with E2, which can often give the less substituted alkene. E2 may give this, because E2 has some very precise requirements. By the way, the less substituted alkene in the context of this elimination is called the Hoffman product. And these are chemists who recognize this and whatnot. These products are later just named Hoffman. That's spelled right, I believe. It's with two N's on the end. Okay, examples. Here's an E1, and we've already kind of looked at this. If you take this guy and just heat it in water, or your choice of really any solvent, you actually don't even have to use solvent. It'll eliminate by an E1 mechanism, and you'll get this product here. Theoretically, we could get two different products because we have an HA and an HB. We have two different types of beta hydrogen. We could put double bond in between here, which is what's shown, or we could put double bond in between here, which would be that. Okay? Two possible beta elimination products. Well, which one is more stable? That one, tri-substituted alkene versus monosubstituted alkene. If I'm telling you we're doing E1, which do we get? Most stable. Boom. That's the most stable. Now, does this have an isomer? No, it's not stereogenic. So, if it did have a possible, which would be better, cis or trans? Trans. Or if it's multi-E. E means your biggest groups are opposite. But that example doesn't have stereochemistry, so only when isomers are possible do you have to worry about that. Not every alkene has stereochemistry. Now, of course, you also make here, I showed H3O plus and Br minus, because if there's nothing here, you form what? That plus HBr. Well, if water's there, okay. So you can do this mechanism, you can ionize it off, a cation. Then the water could act as a base, or bromine, either one. But water acts as a base, move this in, then you form H3O plus and the Br minus is just there. Now you could just form HBr, but since we have water, how is HBr going to exist? exists like that, right? HBr in water exists. So that's why I showed it like that. That's how it's going to exist. So you can't just use your base. But it's a weak base. If that was a strong base, we'd be doing E2. Okay. E1 always gives Zaitsev product, not the Hoffman. Did I draw it? I think I erased it. Okay. What about E2? E2 varies. E2 varies. E2 does not always give the Zaitsev product. Now, when you're doing an E2, when you're doing any elimination, no matter what the mechanism you use, typically the system would like to give the most stable product. And that, by default, that's what you want and the system strives for. But sometimes there's reasons you can't get it. In the first example, there's no reason you can't get it. It's going to give the most substituted. For example, if you take this with hydroxide, which is a strong base, there's two different beta hydrogens, HA and HB. To get the alkene, the more substituted one, the base takes this H, these electrons move in, kick off the leaving group, all concerted, we didn't make a carbocation. And this would give what? We give that, E2, all together now. Here's one thing you have to recognize about this. Which beta hydrogen is more accessible? Or I could say, which H is more sort of buried and hidden? Do they look different in terms of accessibility?
Yes.
HA is actually in here between these two methyl groups. HB is more open. Which is the base going to be able to get to? Easier.
B.
HB. Yes. That's important. But if we take HB, do we get the most substituted alkene? Or would the double bond be down here and it would be less substituted? Okay. So there's sort of, okay, it's more accessible, but you don't get the, okay. Well, here it is. We get the best alkene as long as the base is not too sterically hindered. If your base becomes very bulky like this, it's going to have a tough time getting that HA. And the more bulky your base gets, the more prone it is to taking HB. And that's what I'm showing down here. If you do this reaction with a more bulky base, now it's not on the atom here, but it's next door and it's still bulk. This makes it more difficult to get to HA, and the reaction starts producing product coming from the base taking the more accessible H. And you actually get the double bond here, which is less substituted. It's called the Hoffman product. Because we had a bulky base. And ultimately, if you dig into why, the reason is because this is so bulky, the transition state of this, grabbing this H, is apparently just prohibitive. It gets too high. Okay. So Anna, you have an H. Hold up your H. Okay. And over here, you hold up your H. Okay. Well, I need one here. Because you're not quite accessible. Okay. Hold it out here, really accessible. Okay. All right. If I take her H, I'm going to get the best alkene, but I can't get there because these methyl groups are in the way. Boom, this is much easier. That's a high activation energy. I take this H and I deal with getting the less substituted alkene. But remember, the transition state is actually what dictated the pathway. Now, if I'm bulky, I'm going to have a more difficult time getting to that H. Okay? I just can't get to. But if I'm real small, maybe I can squeeze through here and I can do it. That's what we're doing here. Take home message. The more bulkier your base is, the more prone you are to getting the, what is that? Hoffman product. By the way, the Hoffman product is known as the kinetic product. It's not the most stable. Zaitsev is the most stable, thermodynamically most stable. This is called the kinetic product. Why kinetic? That refers to rate. Right here. If we're crowded, is the base going to be able to get to that H quicker or this one? Boom, this is quicker. You get that product. It's not the most stable product, but it's the fastest form product, which is known as the kinetic product. So, and this is known. If you try to do these reactions with a bulky base, you'll start getting that as the major product. Okay, what's another reason you might get the kinetic product or Hoffman product? Now this one is the more commonly referred to. This is a big one here. It's a stereochemical requirement for an E2. Whenever you do an E2 elimination, let's read it here. The leaving group and the beta hydrogen that's subtracted must be coplanar. With anti-coplanar, which is also called anti-periplanar, much more preferred over syn-coplanar. If the leaving group and the beta hydrogen cannot become anti-coplanar, then the beta elimination will be very difficult. Or basically for us, we'll say it won't occur. It can't occur. Okay? So not only does the H have to be there next to the leaving group, these have to be oriented a certain way in the E2 elimination. Not in E1. E1 doesn't have this requirement. Only E2. What is anti-coplanar? Here's the carbon leaving group, here's the beta hydrogen. Like this, remember Newman? Okay, and actually a model would be good. Revisit this. Let's say this is a carbon with a leaving group, bromine or chlorine. Here's a beta carbon and hydrogens. Let's say there's 3 here, but let's just call this is beta hydrogen. Eliminate, put double bond in here, and kick the leaving group off. Remember, we got free rotation. How does the H in the leaving group have to be when we do the elimination? Remember, when we do an E2, everything happens at the same time. Base takes the H, electrons move in, this moves off. How do they have to be? Anti-coplanar. Anti and coplanar. You see how this and this are in the same plane? If I hold up a sheet of paper like this, one sheet of paper, there's your plane. What if the H is there? Are they in the same plane? No. The leaving group's in the plane, but that thing's pointing forward. Anti-coplanar. What do you call that? Syn-coplanar. It's like syn isn't synonymous with cis. It's cis-coplanar. It can eliminate that way, but it's more difficult. Most highly preferred is anti-coplanar. And so here we go. The base comes in, bonds to this. These electrons move in here. That gets kicked off all at the same time. Importantly, you should see that that is, if we put the leaving group, that's that, right? Bromine up, and on the back carbon, the H is straight down. Remember your Newman projections? Okay? That's just sort of generically shown, that versus that. Okay? Importantly, rings. Look at these two. This is the same compound. This is just different conformations. Here the bromine is axial. Here it's equatorial. Now, this is symmetrical, so these H's are really the same as these. Let's focus in on these here. Which one of the H's is anticoplanar to the bromine? That one. Bromine is straight up. This one is straight down. Not that one. These are anticoplanar. Not those two. Over here. Focus in on just the H's on this carbon. Which H, top or bottom, is anticoplanar to the bromine? Neither. Neither. The only time you have an H that's anticoplanar to the bromine, the leaving group, is when the leaving group is axial. When the leaving group is equatorial, the beta hydrogens, none of them are anticoplanar. What this means is, in a ring, when the leaving group is on the ring, the leaving group has to be axial to undergo an ethyl elimination. Because only when it's axial is the beta hydrogen anticoplanar. Now, why does it have to be anticoplanar? It's almost like when we do backside attack, we come in backside. Something bonds to the H. These are electrons. Here's the nucleus. The base takes the nucleus. The electrons, then, okay, I'm going to move them in. Take the H, take the H. So the nucleus is gone. The electrons move in here. And look at this here. They're coming in sort of backside to the bromine. They're kind of moving in here, backside. Now, if this was like this, and you take the nucleus, these would be moving in not backside, they're side side. Okay? Now, if it was syncoplanar, take the H, and the electrons are moving in almost like, it actually does work here because there's complex things that we don't get into higher discussion. But the most obvious, and the one that works best, is for these electrons to come in here, sort of backside and kick off that lever. So that's the genesis of why this stereochemical requirement is there. Okay. Now, we dive right in here. We take this, treat with KOH isopropanol. What's the product? First off, is it going to be substitution or elimination? Because once we get to the end of this discussion, we're going to see that either can take place potentially, and we're going to have to decide first. We're doing a substitution. Is the OH going to just replace the bromine and give us a substitution product? Or are we going to do a beta elimination and make an alkene? Who's got the answer? That's pretty straightforward here.
Is it a beta elimination?
Why? Yes, why?
Because the carbon where the leaving group is tetrahedral and it's tertiary.
It's tertiary. And you don't do SN2 on a tertiary halide. What about SN1? Sure, SN1 is good, but our nucleophile is strong. It's a bully. It's not going to sit back and wait for ionization. Strong base / nucleophile bimolecular. Your choices are only SN2 or E2. You don't do SN2 on this substrate, so by default, what are we doing? Okay, we're doing E2. So that's how you're going to have to get to that point. Now, how often have students say, but isn't that a weak base? Sure it is, but here's a strong one, and that's the one you need to be looking at, the strong one. This here is just solvent in this case. And alcohol can't just be a solvent. So E2. So since it's E2, okay, how many theoretical alkenes can we make? Regio.
Just two.
I have an H here. I'm going to draw in the stereochemistry. There's HA. That's a beta hydrogen compared to other, okay? Alpha. Here's a beta carbon. Does it have an H?
No.
No. Are there any other beta hydrogens?
The one, the methyl.
Yes. This methyl. Just because it's not in the plane doesn't mean it doesn't have an H. There's an H here. And we can put the double bond between that carbon and that carbon. Now, to get the Zaitsev product, which H would you remove? HA. HA would give you a more substituted alkene. Let's draw the alkene. If we removed HA, we would have double bond here. This becomes planar. You have a methyl and a T-butyl. And up here you would have an ethyl and a methyl. So I'm just going to say minus HA. But you could also have stereoisomer because this is E. But you could also have Z. You could have the two big groups on the same side, theoretically. Now if you removed HB, you would get, I'll draw it over there, maybe on paper, leave this for the answer. Double bond here, T-butyl on that carbon, and then a boop, boop. And we maintain stereochemistry here. Put double bond here, we get this alkene. It's disubstituted. This is tetrasubstituted. This is going to be Zaitsev. This is Hoffman. Does it have a stereoisomer possible? No, that alkene's not stereogenic, is it? It's just trans there. 3 possible theoretical products from beta elimination. This has a stereoisomer for the third. So we determine we're doing elimination by E2. Here are our theoretical elimination products from beta elimination. Which one do you get? Okay, which one would the system like to get? Which one's thermodynamically the best? This. Tetrasubstituted and E, big groups opposite. But do we get that? What's the stereochemical requirement for the elimination? We need to look at that. But before we look at that, let's look at the base. If this is sterically hindered, it's going to start favoring, which one's more accessible, HA or HB? HB is more accessible. Is this a sterically hindered base?
No.
No, it's not. It's one of the smallest bases you can have. So here's the take home for that. That's not going to have any trouble getting HA. It's not sterically hindered. You'll recognize sterically hindered bases. They'll have lots of substitution around. If it's not sterically hindered, let's go for HA because it gives you your best product. But we're still not done. Is it going to give E or Z? Yes, E is most stable. That doesn't really matter here. We've got to have These two need to be anticoplanar. Are they anticoplanar as drawn?
No.
Well, here's where I'm going to take this back to Newman projections, because I could show you here, and then if this is tweaked a little bit, I'd have to show you again, and then I don't think there would be so many variations. The best way to answer that question is to draw that in a Newman projection. If you draw it in a Newman projection, it's more easy to see when they're anticoplanar. Because that's what we want. Just let the stuff there. We're out of time. Draw this in a Newman projection. Once you get it drawn, look at that H in the bromine and say, are they anticoplanar? They may be, and then if they're not, you need to rotate things and make them anticoplanar. Then the elimination can take place and things will end up just where they were at that point. We'll do that on Monday. But first, draw that in a Newman, like we did 6 weeks ago. And look at your H and Br, the relationship in the Newman that you draw. And consider rotating. Okay, I've got group labs. I'll return these to the corresponding author. I don't know if you, some of you guys, everybody was corresponding author, and in other papers there was no corresponding author. Corresponding author is, here's one that had a corresponding author. Ryan Amon. Okay. I'll just call the first name Rebecca Childress. Stop.